Okay, class. So now we go to the next part, which is part E. Okay. So now we look on the series magnetic circuits with the given I. You have to find the flux. Okay. So now we look on the converse problems. Okay. Given an I and find the resultant flux. Okay. So for the case of a core with one material and constant cross-sectional, so this is straightforward. Okay, but for the circuits which have two or more sections, okay, the process is not so simple because before we finding the H is any section, you need to know the flux density, AB. However, in order to determine the B, okay, you need to know the H. To get around this problem, okay, the practical use is by using the try and error methods. Okay, so we see, okay, on the example 7, okay, so the following circuits, okay, which have the n number of, which has the n turns is equivalent to 25 turns, and the given I is 10 ampere. So you have to determine the flux. Okay, so in previous, okay, examples, okay, is given, the question gives you the flux and you have to find the n or the current, right? Okay, so now it's inverse. Okay, they give you the n and the I, and you have to find the flux. Okay, so for this type of the series, okay, the series section of magnetic fields, okay, so you have the flux, okay, the same flux here, okay, you have this coil with the number of n turns, okay, which is 25 turns, and the current is 10 ampere, okay, will produce the flux, okay, flux on the cast steel core with a sectional area of 0.01 meter squared. Okay, so the first step, okay, you draw the equivalent ampere circuit law using the right hand rules. Okay, so the equivalent circuit law here is the Ni here, okay, and the direction of flux is from, okay, is going up, right, okay, around this circuit, okay, and then you have the HL cast steel here, okay, so which give you, okay, the Ampere's circuit law equation give you the Ni is equivalent to HL. Okay, you find the H using the Ampere circuit law. Okay, so the HL is equal to Ni, right? So the H is equivalent to Ni divided by L from this circuit equation. Okay, so which equivalent to 250. Your Ni, okay, is N times with your I. And N is 25 and the I is 10 ampere, so you get the Ni is 250 divided by, okay, the length, okay, is 0.2, okay, and you get the H is 1250 ampere turns per meter. So you have to determine, okay, the B, okay, for the cast steel from the pH curve. Okay, so from the calculated H just now is 1250. Okay, okay, you see or you refer, okay, at the cast steel because the curve from the cast steel. Okay, so we refer to the cast steel curve. Then from here you get the B. The equivalent B is 1.25 Tesla. Okay, and then the next step, okay, you have to find the flux, right? Or you can use, okay, the equation B is equal to flux divided by area. Okay, so the flux is B times with your area. Okay, the flux from the pH curve, okay, that you get right now is 1.24, okay, times with your area is 0.01. Okay, and then, okay, is equivalent to, okay, so this multiplication B and A, okay, give you the flux at 1.24 times 10 power of minus 2 Weber. Okay, because the given area is, in the question, okay, is equivalent to 0.01 meter square. Okay, so now we look on the example 8. Okay, so you still have a cast steel, okay, material for this magnetic core. Okay, but now we including the gap. Okay, we have the gap here. Okay, so the question now, okay, give you, okay, the Ni is equal to 1,100 ampere turns. So you have to determine the flux in the core. Okay, the cross-sectional area is given as 0.025 meter squared. Okay, and then the length is 0.2 meter. Okay, and then you have to find the flux. Okay, so the solution, okay, is by try and error. Okay, so the Ni, okay, is given as 1,100. Okay, so the first step, okay, you have to draw the equivalent ampere circuit law. Okay, so the equivalent ampere circuit law, okay, is the Ni here, okay, with the flux flow, okay, the series flux flow in the circuits, in the closed loop circuits, okay, but you have the drop, okay, the MMF drop here, which are the H and L steel, HL steel and HLG. Okay, so the next step, we use the initial gas. Okay, so we can assume that 90% of the MMF appear across the gap. Okay, with the applied MMF, okay, in the question is 110, sorry, 1,100, okay, ampere turns. Okay, so we assume, okay, the 90%, okay, of this, okay, flux, okay, for the gap, okay, which 90% of the applied MMF is about 990, okay, ampere turns for the flux. Okay, and then the Hg, okay, from this formula, the Hg is the MMF of F, or the Ni divided by L. Okay, so we know that your, okay, your flux here, or the flux G, okay, the flux is equal to the flux G is equal to 0.9 of the Ni, okay, which is equivalent to 990 divided by your length. Your length is, how much is 10% of 0.2? It's also 10%, right? Okay, so 10% of 0.2, okay, so give you 0.02 for the length of the LG, the length here. Okay, so you have, okay, the Hg, okay, is 4.95, okay, times 10 power of 5, okay, for Hg. Okay, thus, okay, you can get your Bg, okay, your flux density of the gap is mu naught Hg. Mu naught is 4 pi, okay, times 10 power of minus 7. Okay, the mu relative is 1. Okay, so mu, okay, so you will get your mu is 4 pi times 10 power of minus 7. Okay, and your Hg, okay, what you obtain right now is 4.95 times 10 power of 10 power of 5. So your Bg is equivalent to 0.62 Tesla. Okay, so this, okay, for your Bg, thus, okay, we can have, okay, your Bg, okay, is 0.62. We know that sharing the flux with your steel, okay, So we can say that your BG is equivalent to B still. Okay. So from the cast iron of BH curve, okay, you can know, okay, your B still, okay, at 0.62 Tesla, okay, here for the cast steel, okay, and then you project A in order to get the respective hash steel, which give you 400 ampere turns per meter. Okay, from these two values, then you compute the nu and I. Okay, so we know that your Hg right now is equal to 4.95 times 10 power of 5 ampere turns per meter, and the length for the gap is 0.02. Okay, and the H steel, okay, we observe from the BH curve is 400 ampere turns per meter, and with the length is 0.2 meter. And then we know the summation from as referred to the ampere circuit law. Okay, so the Ni is HL steel plus HLG. The summation of these two, HL, will give you 1070 ampere turns, which as referred to the applied MMF is 1100 ampere turns. So we consider this is the acceptable value because the answer is about 2.7% lower than the applied NI. So then we can calculate the flux with this using this formula. B is equal to flux divided by the area, and the flux definitely is equal to B times with your area. The B is equivalent to 0.62. That's what we determine right now. So times with your area. Area of the core is 0.025. So this this multiplication of the two components give you the flux which is equal to 1.55 times 10 power of minus 3 Weber. Okay, so now I stop here until we proceed to the part F later. So thank you.